Okay. Yeah, so I will switch topics a bit and talk about something that's not really defense related, but more fundamental physics. So yeah, as Bellman mentioned earlier, there was a prize for space-related master thesis, and I was lucky enough to receive it last year. So I will be giving a quick overview about what I worked on. So this is more on particle physics and particles that come from space and onto Earth, and then we can detect them here. So, first of all, just a quick introduction about me. So, I graduated from here, KTH, in the engineering physics program last year. And then I now study at the ETH Zurich in Switzerland, and I'm doing a PhD on particle physics at CERN in Geneva. So if you ever pass by, let me know and I can show you around. And I'm working with a particle called neutrinos that are very tiny particles, very hard to detect, but you'll hear more about them in this talk. So first of all, just to give an overview, uh, you all know about the periodic table probably, but then the periodic table is made out of atoms, and atoms themselves are made out of even smaller particles. You probably know about electrons and then protons and neutrons. These protons and neutrons are also made out of even smaller particles called quarks and gluons. And when you take all of these fundamental particles that are the tiniest constituents of everything in the universe, you have these uh, 17 particles. And this is what everything that we know about is made out of. And so this is what particle physics is all about. And what I am working with is these three particles here. These are called neutrinos. They do not have any electric charge. They only interact via the so-called weak force, which, as you can tell from the name, is pretty weak. So it doesn't interact with a lot of stuff. There are billions of them passing through you right now, and you don't feel anything. There are three different types, and they can actually mix between different types. And one of these flavors, so-called, of neutrinos can mix into another flavor. And they're also very important for understanding how radioactive decays work, how the universe began, uh, how the stars produce light, and many other things inside the universe. Yes, and the one to the very right here, the tau neutrino, is the one that we know the least about. So this is the one that I have been working on mainly. So this is the only equation I will be showing in this talk, so don't be too scared. This describes how you transition from one type of neutrino to another. So it's essentially just a wave, and then depending on how far you are along this wave, it will be a probability that it transitions from one neutrino to another. And you can kind of ignore everything besides these two parts, which is the L is just the length traveled by the neutrino, and the E is the energy. So the longer it travels, you will be on different places along the wave. And then if you have a higher energy, this wavelength will be longer or shorter, depending on the energy. So how long is roughly this? What's the scale of this? It's about the size of the Earth. So if you have a neutrino hitting, or if you have a particle hitting the atmosphere, creating a neutrino, this one will then travel, well, they will travel in all kinds of directions, but some of them will travel through the Earth, um, and this, so several thousand kilometers. And during this time, they will oscillate and switch from one neutrino to another. And once they hit the south pole here, they might, if you're lucky, interact, and then you can measure the new neutrino that has been created, that it has transitioned to. So at first, you mainly create one of them called muon neutrinos, and then after traveling through all of the Earth, you will have a certain amount of tau neutrinos. But we don't know a lot about neutrinos, and especially tau neutrinos. So what we're trying to do through many types of experiments is to understand how many of these tau neutrinos are created, or how often do you transition from a muon neutrino to a tau neutrino. So that is what an experiment placed at the South Pole called IceCube is working on. So to detect neutrinos, since they only interact through this weird weak force, you need either a lot of neutrinos, a lot of patience, and or a very big detector, ideally all three of those. And that is exactly what IceCube is. So you can see the Eiffel Tower down there in the bottom right. That's about the size of this detector. So it's a cubic kilometer of ice. So instead of, this is of course impossible to build as our human race right now. But what you do is that you just use the ice on the South Pole. So this is actually a very crystal clear ice that has been compressed for a long time. And then you can use this as a massive detector where if this particle hits the ice, it will create light. And then you can measure this light inside the ice by just placing light sensors. So the only thing you actually need to build are these light sensors. And then you can have this massive detector. It's called Cherenkov light, this light. So then you also have a sub-detector inside this detector that's marked with deep core here. This is where you have a higher density of these light sensors called DOMs. And there, since you have a higher density of them, you can detect fainter light, and therefore you can detect weaker, lower energy neutrinos. And this has been the focus for me. So this is roughly what it looks like when you have a neutrino hitting the ice. So the neutrino would, so here the size of the blobs, the balls, is the energy or the amount of light. The color is the time. I don't remember which color is what, but I think it came from the right side here and then passes through the detector. And then after, as time passes, these light sensors would light up and detect light. And then you can see a particle traveling through the whole detector. And then you would see, you would be able to say that this is a neutrino. What I looked on specifically is the tau neutrino. So the way the tau neutrino works is that you have it, you have the tau neutrino, this Greek letter nu, coming in from the left side. It interacts with a nucleus. So in ice, it would mostly be hydrogen or oxygen. And then it would destroy this nucleus, which creates a bunch of new particles. And it would also create a so-called tau lepton. This is essentially an electron, but a lot heavier. This one would then decay within a trillionth of a second, so doesn't live for a very long time. And then when it decays, it creates a bunch of new particles, and these particles would then generate light inside the ice, and this is something that you would see in the actual detector. So you never see the actual neutrino because it has no electrical charge. So it needs to hit something and then create other things that can create light. And so the way that these experiments are done is that you simulate how this interaction happens. You estimate based on the simulations how much light you would see in the detector. And based on that, you compare with your real data to see if you see something similar. So understanding this light here that is generated and consequently the decays and the particles that are created, you need to have a very good simulation. Yes. So just to have recap what I've said so far, this tau neutrino is something that we don't really understand. IceCube is one of few experiments that can actually study these particles. And it's very important to have good simulations of the decays of these particles and specifically the tau lepton to understand how we can how to search for these particles. Okay, so now I had a portion that is quite technical. I think I will just give an overview of it to not bore you with the details. But essentially, uh, the simulations that were done in IceCube had a few issues that I discovered. So first, I investigated if the decays of this tau lepton, how they were being performed inside the simulations for IceCube. And this was then, I then uh, investigated and compared this to a, uh different simulation software. So what was used inside IceCube was something called Giant4, and this is the top row, and then a different software that I was comparing it to called Taola. As you can see, roughly qualitatively from here, had much better simulations of this tau decays. So uh, I then wanted to compare, okay, qualitatively, there are a lot of more features that are important for simulating this decays inside one software than the other. But how does this quantitatively compare between these two simulation softwares? So this was something that I investigated during my master thesis. I will skip some of the details. So one example that was not implemented in one of them is something called polarization. So this is when you have the tau lepton that these particles have something called spin, where they spin around their own axis. And this affects how it decays, because this is similar to how energy always needs to be conserved when you have a ball hitting another ball. The total energy of that system must always be conserved. If you have polarization, the spin before the decay and after decay also needs to be conserved. So this affects how the decay products that are created from the decay move around and their energies. So when you plot the, okay, so this is, for example, an example of where I quantitatively compared the decays of one software and the other one. So you can ignore most of the curves, but the most important ones are the blue ones and the red ones. So the blue one is the one used inside IceCube before, and the red one is the one that has a more realistic simulation with more features. So you can see that, and this is the fraction of the energy on the x-axis that goes to the particles that actually create light. So if you have a tau lepton with something x amounts of energy, then the fraction of that energy that goes into a particle that actually is visible inside the uh, ice would be the x-axis. So let's say half of that energy uh, is sometimes you would have half of the energy being visible, sometimes you would have closer to zero. And you can see that without this polarization, you would have more energy. So the blue curve is shifted more to the right than the red curve. So you would have more energy being visible. So you would overestimate the energy that you actually see inside the detector. I will skip some other details. There was another issue as well with the simulations where once you have this decays, it's usually the tau lepton decaying into another tau neutrino and then one more particle. And this would then, so this is how you illustrate it. You have the tau lepton coming in from the left, splitting into two particles. You don't see the neutrino because it has no charge, but you would see the other one, which would then decay into other particles. this is similar for other decays. However, in the previous software that was used, it was not simulated like this, but instead you just split it into all the free particles that, so in the top simulation, you simulate it in steps of one particle decays to another, which decays to another. Whereas in the bottom row, you just split it so it decays to all free particles immediately. And this also affected the energy distribution. I will just give one example. So here you can look at the distributions of the energy that goes into the particles that you actually see in the detector. And you can see that there's quite a large difference in this plot between the red curve and the blue curve. And again, the blue curve is shifted more towards the right, so you have an overestimate of the energy. So your simulations would predict a higher light emission inside your detector than you would actually expect to see once you uh, try to find these tau neutrinos. Okay, I will just go to the summary. So this, what I investigated was that here you have a lot of different ways that the tau lepton can decay. So it can decay to a lot of different types of particles. And the numbers on the right side just shows the probability that it decays in one way or in another. So I found that these ones that I've highlighted in red here are the ones that were kind of problematic. So you can see that it's quite a large fraction of all the decays that were a bit problematic. And this has now been, okay, sorry, I think this was an unrelated slide. Yeah, so about 65% of all the decays of the tau lepton were a bit wrong in their simulations or their implementations. So this was something that I then improved, suggested to this IceCube collaboration, and they then implemented it into their simulations and could study tau neutrinos more effectively. So yeah, so after this was improved and added into their simulations, my master thesis ended there, but the work of all of IceCube did not end there. Instead, they continued analyzing data, upgraded their detector, and so on and so on. And they have recently published new promising preliminary results. So this shows roughly the number of tau neutrinos that they observed divided by the number of tau neutrinos that they expect. So if you observe the same number of events as the same number of particles as you expect, you would just have a point at 1. And then the important part here is the error bars. So the bar around the circle is the error bars. And you can see that the previous result from 2019 had a lot bigger error bars than the result from 2025. You can also compare it to other experiments that are in the bottom rectangle here, which also had very large error bars. So this is, of course, from a multitude of reasons from a lot of people, a lot of researchers that have worked hard to make this bar as small as possible. But one of these contributing factors was then this improved tau decay simulations. So this is, as you can see, compared to other experiments, by far the most precise experiment and observation so far. And yeah, I contributed a tiny fraction to that. Yes, so just to conclude, tau neutrinos are very exciting. They're important for the universe and understanding how the sun works and all the stars work. We don't know essentially anything about them, but there are a few experiments. For example, IceCube, which just uses a cubic kilometer of ice at the South Pole to study these particles. And during my thesis, I improved some of the simulation software to make it easier and more precise to try to find these tau neutrinos. And new preliminary results that have been presented this year by the IceCube collaboration shows that they now can study these tau neutrinos at much higher precision compared to before. Yeah, that's it, everything from my side. Thank you.
Thank you, Simon. And it's very good to see that you continue research in this area as a PhD student. So, do we have any questions from the audience? In the back.
Also someone to the right.
Up to the left first.
Yes, that's a very good question.
Please repeat the question.
Yes, sorry, thank you. So the question was, what would be the consequence of this measurement not being equal to 1? What if the measurement was 1.5 or 2 or something else? So this would mean that there's something we don't understand that's not correct with our current knowledge about particle physics and theories. And this might sound bad, as in, oh no, there's something that's incorrect with our models. But this is actually very exciting because that means that there's something beyond what we know, and maybe there's a new exotic particle, and when these oscillations happen, it does not only oscillate two tau neutrinos, but also something else. And that's why we see fewer tau neutrinos than we expect. Or maybe there's some other particle that's coming in and that one oscillates and create tau neutrinos as well. And that's why we see more of them than we expect, and so on. So the question was, you're probing, sorry, could you repeat your question? Okay, so the question was, are you primarily studying the neutrino oscillations or the production of tau neutrinos inside the atmospheric showers from cosmic rays? It's primarily neutrino oscillations, not the atmospheric showers. Yes.
Yeah, thank you very much for the presentation. Very impressive work. You mentioned that you discovered this shortcoming in GN4, and I wanted to ask if this has been reported back to the GN4 team and if it will be fixed for like future versions of GN4. Thank you.
Yes, so I did report to them. What they said was essentially, okay, that's good to know, but we don't have time to work on that. So yeah, but they would just add a disclaimer into their documentation that, yeah, this might not be that accurate, so please use this instead, or something like that.
Thank you. Another question?
Hi, thank you for your very interesting talk. I have a question about the error bars here, or the 1 sigma. Is that how it is now, or how it was with Giant4?
The yellow bar is with Giant4, so the one IceCube 2019, parentheses 3 years. That one with Giant4. The top one with the red 2025 result is with the new simulations.
I mean the 1 sigma, is that the confidence or the and if so, for which one of the, is it the Giant4 confidence level, or is it for the new one?
So the yes, the error bars here is 1 sigma errors on the measurements. It's not necessarily just the Giant4 versus Paola or other simulation effects. It's a lot of effects, like, I mean, other stuff like trying to understand how much dust there is in the ice and how that affects the light, and how we model the air showers from cosmic rays. So there's a lot of stuff that's makes
So it's for all of them, or
for all of
okay.
them combined.
Yeah,
Yeah.
thank you.
Yes, there is more data. That is probably actually the biggest reason why the error bars are smaller.
Thank you. Any more questions? I see one down here.
Yes, thank you for your talk. It was very interesting. I was also wondering for this final slide. I know at least Super Kamiokande detects solar neutrinos mainly, right? So is it really fair to compare the precision with IceCube, which mainly focuses on other kind of new neutrinos?
Yeah, so these results are okay. I could be wrong. I'm not entirely sure about the Super Kamiokande result here, but I'm pretty sure that it's also from atmospheric neutrinos and measurements that they've done with that. So they can do other types of measurements. Depends on what you mean by fair, as in that's their latest measurements. But yes, usually they would not be able to make as high precision measurements because they have a smaller detector, so they can't observe as many neutrinos, for example. But I would say that it's a fair comparison.
Okay, thank you.
Yeah.
Was there another question? Two more questions. Okay.
Thank you. Feels like us particle physics people are stealing the show here from the space. But I wanted to ask a follow-up to what you said about the statistics. So did you try the new analysis on the old data set, that 3-year data set, just to see how much of the error bar is coming from the statistics and how much is coming from the precision and the simulation? So the Giant4 or the other one?
I have not tried that, no. But I'm confident that the other people within IceCube have checked how much does each uncertainty contribute to these error bars. And they have a long table of that. Though right now everything is preliminary, so as far as I could find, there were no other like detailed results that I could show besides just this plot. So I don't have it here.
Thank you. And last question before the break, and Simon will be around for any more questions, so you can continue the discussion. And I also have some information after the last question.
Yes, I'm just wondering, because you said there are like billions or trillions of neutrinos going through us all the time. How many do you detect? So what?
The fraction of them they
Yeah.
detect, or in IceCube, I am not sure. It's 0.00 with a lot of zeros % of events. Usually, it's maybe like I think roughly 1 per day or something like that. So that's the order of magnitude. So yeah, you can try to make the math where you take 100 billion and then per second and then divide it by, yeah. So it's a very, very small fraction.
Thank you. So let me switch back to my slides. Yeah. Thank the speaker again, definitely. Very pedagogical presentation.